Chapter 4 in general is about polynomial functions, which are like these here, which you could break down farther into specific types if you wanted to. And linear functions, we had a whole bunch of stuff with those toward the beginning of the course. Quadratic functions, that was basically the last chapter because those are parabolas. Like graphically, that's what they are. And then you can go higher up in terms of the degree. So linear functions, those are degree 1, or that's the highest power of x that shows up. Quadratic functions, those are degree 2 because there's the highest power of x right there, that 2. But you can go higher, you can go to cubic or to quartic, right? And quart, like 4, so the highest power of x that's there is a 4. Quintic would be 5, and we do occasionally have those show up, but I don't think that term is one that you really need. So going down here, there aren't going to be any restrictions, right? There's no square root, there's no division, so you couldn't have any division by 0, right? There's no x in the denominator anywhere. So there wouldn't be any domain restrictions, and therefore the graph that you get is a smooth curve that's all connected together. So then going down a little bit, the cubic functions, they can be relatively simple looking like this one on the left, but you can have stuff going on in the middle. So like how this one has a hump, it's got a peak, and then it's got a valley. And so does this one, but it's more pronounced. So you can have those things. One thing that will always happen with cubic functions, this is actually a big part of this section, is that on one end it will go upward and then the other end will go downward. So that's happening in all three of those. That's always what happens. That's actually always what happens for any polynomial of odd degree. So it would work for linear functions, it would work for quintic ones too. And then the quartic functions, so this would be degree 4. You can have ones like in the middle where that kind of looks like a parabola. It's supposed to be slightly asymmetric. It's not that I drew it badly by accident. But you can have ones that basically look like that. Or you can have ones with extra stuff going on in the middle, like this one on the left where it's got this extra hump. And then you got this one on the right where this left side is kind of wavy. You got some extra things going on that you wouldn't have with a parabola. So yeah, if you have a higher power of x, then you can have a more complicated looking shape. That part, it seems like it would make sense. And that's certainly a thing that you can have. But the other thing that's worth pointing out here is notice on the ends, they always point in the same direction. So like the one on the left, they're both pointing up. One in the middle, they're both pointing down. One on the right, they're both pointing up. And for every quartic function, that's the way it works. And for every function of odd degree, that's the way it works, right? That's the way it works for parabolas too, right? Parabolas, either both ends point up or they both point down. It would be the same thing if your degree was 6 or 8 or 10 or so forth. The next thing with graphs would be extreme values. And there are two types of these. You could have absolute extreme values, and you can have local or relative extreme values. So sometimes a local max or a local min is just called a relative max or relative min. Our book uses local, so we'll stick with that. Those terms are basically interchangeable. An absolute max or an absolute min, that would be a situation where a function either has a highest point or has a lowest point. And then what are these local maxes and local mins? Well, that's where you would have either a peak or a valley, but there's some other point on the function where you can have points that are higher or lower, respectively. And this is much easier to see graphically, but in words and symbols, this is what the definitions would be. And it's true that an absolute max would also be a local max and an absolute min would also be a local min. But typically, if you had an absolute max, you would just call it an absolute max, right? And then if you have a local min, usually, if you're calling something a local min, that means that there is something lower somewhere else. But that's a valley that shows up in the function somewhere. So to go down to this picture, where if we want to identify all the extreme values, all right, can I get all the labeling up here at once? Sort of. There. Okay. So with this one, this appears to be a function of even degree because on the left side and the right side, both ends are going upward. But notice how this works. So the one that's the absolute min down here, that's the absolute lowest point of the function, right? Like this is a valley here in this part of the function, but there's no point anywhere else that's lower than that. That's what makes that the absolute min. And the difference between that and the local min over here, because you go, yeah, this is a valley as well. But there is a lower point on the function below this one, right? I mean, you go, well, you got this stuff down here, right? This is lower than this thing. So that's why that's a local min, or just a local min, because there are other points that are lower. And then the local max here, right? That's a peak, right? Like that's a hump, but there are points that are higher, right? Over here on this side, over here on this side, you get a whole lot of points that are higher. So that's not going to be an absolute max, because there are points of the function that are higher than the top of that hump. Or with another example, and notice for this one, the equation ends up being really insane to the point where I didn't even type it all the way out because it just looked really, really wild. But the important thing here is just looking at the picture and figuring out where the peaks and valleys are. This one, it's an odd function, which I guess that's really why I typed this part out. So you can see that leading term is the negative x to the fifth. So that's degree 5, that's odd, meaning that in the graph, you've got to have one end going upward, one end going downward. So there's the end going upward on the left, here's the end going downward on the right. And so that means you're not going to get an absolute max or an absolute min anywhere, because you've got those arrows going up on one end and down the other end. So there's a valley, that's going to be a local min, right? It's not going to be an absolute min because we got lower values over here. Same thing right here. We've got a couple of points right next to each other that the graph plotted, but one of those is the local min. The other one is just an intercept because it just plots those two. You can tell it's just plotting intercepts there, and there. But that's a local min because, again, we got points down here that are below it. And then we got a couple of local maxes here. We got a couple of peaks. But those aren't absolute maxes because over here on the left, this is going upwards indefinitely. So we've got points on the function that are above those local maxes. Another thing going along with the local maxes and local mins is the idea of a turning point, which is where the graph goes from increasing to decreasing or decreasing to increasing. And all extreme values are going to occur there for polynomials. And then a natural question as well, how many turning points should you expect? There isn't a specific number that you should expect, but there's a maximum number that you could have. So it's n minus 1, where n is the degree. So like if you have a cubic function, at most you could have 2. If you have a parabola, you just have 1, right? And that's what parabolas look like. Either they have a point at the very bottom or a point at the very top. Either case, that's one turning point. If you have a quartic, you could have at most 3. If you have a quintic, you could have at most 4, and so forth. So you could have less than that, and that's what this picture is supposed to be about, because that's the graph of x to the 4th minus 1. And you look at that thing and you go, that kind of just looks like a parabola. Yeah, it does. And parabola just has one turning point. So does this, right? Because it's decreasing on the left side, and then once you go through that point right there, then it's increasing. So yeah, one turning point. So with a quartic, a polynomial function where the degree is 4, you could have up to 3 turning points, but you don't have to have 3. You could have less than that. And that's the whole point of having this picture in there, because 1 is less than 3. So yeah, you can have less than 3. Usually it's something like this where it's less complicated, like how here there are a bunch of terms missing, like there's no x cubed, x squared, or x terms. And if you have a less complicated function like that, then usually that's where you get fewer turning points. Terminology. So odd degree and even degree, I've kind of been saying this already, but odd degree is where you have the largest exponent being odd, and even degree is where the largest exponent is even. And then the end behavior, so that's either the two ends going up or down, or one going up and one going down, that thing. So in all these pictures, there's really, that's the only thing that we're going to be worried about, is the end behavior. And this is the key right here, that for any polynomial, the end behavior of this long drawn out polynomial really just looks like what happens with the leading term. So like this one here, the end behavior looks like what you have with x to the 4th. Here, it looks like what you'd have with, well, negative x to the 4th, or I guess negative 1/10 x to the 4th. Here it would be like what you'd have for 1/30 x to the 6th. So notice with all of these that are even degree, the ends do the same thing, right? Both go up, both go down, both go up. And then why does the one in the middle go down? Because this coefficient is negative. So here, the coefficient of x to the fourth is positive. It's 1, and they're both going up. The one on the right, it's 1/30th. That's a little number, but that's still positive. They're both going up. And then here, it's negative 1/10. They're both going down. That's the difference. So both ends are going to point downward when it's even degree with a negative leading coefficient. And then if we go down here to the odd ones, here we have a cubic, we got another cubic, and then there's a quintic, or there's an x to the fifth. And then you say, well, then this should resemble 2x cubed in terms of the end behavior. This should resemble negative 1/4 x cubed. This should resemble 1/100th x to the fifth. Okay, well then notice that this one is going upward on the right, downward on the left. Same thing on the right side, and in the middle it's reversed, where you've got upward on the left and downward on the right. And why is it reversed in the middle? Negative coefficient, right? That's going to flip which end goes up, which end goes down. So if you just think about what y equals x cubed looks like, that goes upward on the right, downward on the left. And that's kind of what happens here, right? It's just steeper because of that too. But it's that same idea, and that's because you've got a positive coefficient here. Same thing here. It's a little number, but it's a positive coefficient. So upward on the right, downward on the left. But here, negative coefficient, so flips around, upward on the left, downward on the right. So the summary, and this is how they get drawn in the homework, which is why I drew them out this way. But if you have odd degree, it's going to be one end goes up, the other end goes down. And which goes up and which goes down is totally dictated by what the leading coefficient is. So if you have odd degree with a positive leading coefficient, then it works like the graph of y equals x cubed, where it's up on the right, down on the left. But if you have a negative leading coefficient, those are going to flip. And so then you've got up on the left, down on the right. The even degree ones, if you think about what a parabola does, that's the simplest thing. That's the way that I think about it. And maybe I'm not being super objective since it is the way I think about it, but I do think that's the way to go. So if you have even degree, like an x squared, x to the fourth, that kind of thing is a leading term, and a positive leading coefficient, then it looks like a parabola opening up, right? It looks like y equals x squared, where you've got up on the left, up on the right. But if you have a negative leading coefficient, like y equals negative x squared, then both ends are going to point downward. So that's like a parabola opening down. So at least then with the even degree, we can tie it back to the last chapter and be like, oh, it works basically like that. And that's true. It does. Okay, then end behavior diagrams, that's where you just draw these things more or less. So this function here, it should resemble the leading term in terms of end behavior. So f of x equals the square root of 14 times x to the fourth. And you go, well, that's even degree, positive coefficient, even though it's kind of a weird number. It's a positive weird number. So then should go upward on both ends, right? There's our end behavior diagram, just those two arrows both going up. Here, odd degree, negative leading coefficient, and it should resemble that leading term, so negative 4/3 x to the fifth. But odd degree means one goes up, one goes down, and negative leading coefficient, that means it's going to be up on the left, down on the right. So you get that end behavior diagram. The other two that are down here, I didn't write out as much, like the resembles part. I just kind of underlined the leading term to signify that's the thing that you want to be looking at. So here, you want to look at that leading term, that 11x cubed. You go, that's odd degree because that's an x cubed and it's a positive coefficient, right? 11's a positive number. So there should be up on the right, down on the left. And then here, there's the leading term, that negative x to the eighth. So that's an even degree, but then negative leading coefficient. So that means it would kind of resemble a parabola opening down. So both ends are going to point downward. The next thing is how many intercepts should you have? Right? We know how many turning points you could expect, at least the maximum number. What about intercepts, which I really mean x-intercepts? So again, this is one where it's an at most, where you could have a maximum, where the maximum number of x-intercepts is equal to the degree of the function. But you could have less than that. And if you have a function of even degree, you could have no x-intercepts like this. You got a parabola where it's entirely above the x-axis and it opens, it's opening upward. That's not going to have any x-intercepts. So you can have that. The most you could have would be 2, right? Which would be for any parabola, because you could have a parabola that went like this, right? That could cross the x-axis twice. But it is possible to have less than 2 intercepts. And I just wanted to point out that for even functions, you can have 0. Right? You could have one that opens upward that's entirely above the axis like this. You have one down here that opens downward, and then you would also have no x-intercepts. But then with a polynomial of odd degree, you've got to have at least 1. So this is a polynomial which I guess, let's see, 1, 2, 3, 4 turning points. That's at least a degree 5 polynomial since it's got 4 turning points. But you have to have at least 1 intercept, because for the odd degree functions, you've got one end going up and one end going down. So it's got to cross the x-axis somewhere. It might only happen once, like this, but you've got to get at least 1 x-intercept for a function of odd degree. Then lastly for this section, matching up functions with graphs. So just kind of eyeballing these, you go, all right, odd degree because left end's going up, right end's going down. This is also odd degree because the left end's going down, the right end's going up. But on top of that, you say, well, this one does what y equals x cubed does, where it's up on the right, down on the left. So this must have a positive leading coefficient. This one must have a negative leading coefficient, right? So just from the pictures, we can figure that stuff out. And then if we go down here, we go, well, those are both even because both ends go upward here, both ends go upward there. I would have to say that C, the degree of it would have to be at least 4 because it's got 3 turning points. 1, 2, 3. So that's the degree of C, it's got to be at least 4. So let's see down here how we can match these up. All right, so if you ignore my writing over here for a second, just look at what's typed. 1 and 3 have to be the first 2 because that's odd, and then 2 and 4 are even. So when we go up and look at those, and we said, well, B was the one where it must have had a positive leading coefficient just because it's going up on the right side. Then we go, well, then B must be number 1 because that's got a positive leading coefficient. A must be number 3 because that's got a negative leading coefficient. So that's how we can piece those together. And then for 2 and 4, we say, well, 2 is a parabola. It can't be this, right? Like it can't be C because this has too many turning points, right? If you have a parabola, that has at most 1 turning point. It couldn't possibly have 3. So 2 has to match up with D. It's got to be this one because this only has 1 turning point. And then 4, it's got an x to the 4th in it. So you could have up to 3 turning points. And I guess at this point, it's process of elimination anyway because we've already figured out the other 3. But yeah, this one would have to be number 4. So C has to be 4. It's got the 3 turning points because it's even, and this one could not possibly be number 2, so therefore it's got to be number 4.